All right, so now we're going to go into part 2 of lesson 3.1, and this is going to be us putting all the transformations together that we've talked about in the previous lesson. So we've talked about how there can be horizontal translations or a left or right movement on the graph. We've talked about how there can be a vertical translation or an up and down movement. And we've also talked about how there can be vertical stretches. So this almost multiplication factor to every y value or every output value. Now, putting it together, we're going to take our vertex form that was introduced in the last lesson and then broken apart, put it all together, and then see if we have a bunch of these different transformations happening, how do we describe them, what is the proper order, and all of that. So let's go into this here. If I was given the original function of this, y equals 2 times x minus 3 squared plus 4, how would you handle these three transformations? Well, we're going to learn there's actually a specific order in which we're going to describe it first and foremost by the stretch or the vertical stretch, this a value. We're then going to talk about the reflections, or if there was that negative value there, we're also going to then talk about the translations or the vertical and horizontal movement. So let's do these in order according to this function. First and foremost, is there a vertical stretch? Yes, and in fact, it's by a factor of 2. So I'm going to write that first and foremost. First bullet point, there is a vertical stretch. So I'm going to start short forming it as vertical stretch or VS by a factor of 2. And then we always want to throw in the statement of it's not only a factor of whatever the a value is, but it's a factor of 2 about the x-axis. Okay, so we've labeled the stretch. Now we want to look for the reflection. Is there a negative value here? No. So in fact, the graph is going to continue to open upwards because we don't see this reflection about the x-axis. So we move to our translations. We have both a horizontal translation and a vertical translation. And here's what we got to remember. When it comes to the horizontal translation, if this is a negative in the brackets here, it's always the opposite of what you see. It's almost like it's lying to you. You're going to hear that probably a lot at the 30 level. It's opposite of what you see. So if this is negative, I want you to treat it as it actually moves 3 to the right. And we showed that last lesson, so go back or see me if you want to go over that. We may even touch that at some point today. So second bullet point, realistically, you could do the horizontal translation or the vertical translation first, either or. So I'm going to say there is a horizontal translation or an HT by, and this has a horizontal translation of 3 units to the right. Okay, now in terms of the vertical transformation or vertical translation in this case, we're going to move up by 4 units because if it's positive here, we just keep it positive. So I'm going to write there is a VT or vertical translation by 4 units upward or 4 units up. There we go. So that's all we have. No reflection, but a vertical stretch, horizontal translation, and a vertical translation. All right, now let's take a closer look at this graphically. So the graph of this function, y equals 2x minus 3 squared plus 4, can be drawn by starting off with x squared and then breaking it apart in terms of we're going to do the stretch, then we'll do the translations, and then hopefully that will be able to give us the new points. Now, something really important here. We always want to first of all plot the x squared graph, or if possible, plot the x squared graph. So down below, I'm just going to plot the original function. If y equals x squared, I'm going to plot this in black and write it as 0, 0, 1 and 1, negative 1 and 1, 2 and 4, and then I'm going to bring it over to negative 2 and 4. And again, we want to connect all these points here, arrows on the end, meaning it extends to infinity. I'm going to do the same thing over here, extends to infinity. There we go. And we could be more accurate with those upper points, but for now, this will be okay. And I'm just going to even clean this up a little bit here. I'm going to put my dot back here and then try to make this just a touch neater through here. There we go. Maybe even bringing that in just a little bit to make it a little more accurate. There we go. Okay, here's the original function, and I'm even going to label it here. So this is our y is equal to x squared. Excellent. Okay, now what we're going to do is we're going to take that new function and we're going to break it apart in terms of the specific steps of which one comes first. And we can actually see that off in the box here. We're going to go stretches, reflections, translations, in that specific order, or SRT. You could call it SMART, but SRT might be maybe a shorter form for this. Now, when we deal with this, first and foremost, we're going to do the translations or transformations in their proper order. So we're going to deal with the stretch. In the case of this one, it gets multiplied by this a value or a factor of 2. So all of these points are going to be multiplied by 2. So we can almost start off with, let's just choose any point on here, and then we'll do those together, and then we can fill in the rest. So if I know that all of them get multiplied by 2, well, 0 times 2 would just keep me exactly here for the new function. But now I think, oh, is there reflection? Nope, because there was no negative out front in front of this function here. So no negative a value means it does not get flipped, or there is no sort of reflection about the x-axis. We know it went 3 units to the right. So I'm going to go 1, 2, 3. And then I'm going to go 4 units up because it was translated 4 units in the positive direction. So this is actually where our new vertex is. And now for the rest of the points, we can actually just do these same steps. What's 1 times 2? Well, it's 2. I move 3 units to the right, putting me over here. So if I go up by that, and I'll even sketch it out with my laser pointer here, 1 times 2 puts me to here. I go 3 units to the right, 1, 2, 3. I go 4 units up, 1, 2, 3, 4. This will be my new point. I'm going to put the dot right there. Now, let's do the same thing for all the other points here. I'm going to start off with my stretch for my -1 and 1 point. So that's going to put me at, from 1 times 2 puts me to 2. I go 1, 2, 3 to the right, 1, 2, 3, 4 upwards, and I put a point here. There we go. I'm going to do the same thing for my 4s. I have a suspicion that it might be off the graph. So if it's off the graph, we're just going to draw our arrows from there. Okay, let's take the example of 4. 4 times 2 is 8. 1, 2, 3 units to the right, 1, 2, and then it's going to be off 3, 4. It would be somewhere up here. So realistically, I could even just put that dot somewhere kind of here just to represent it, and then my other dot somewhere about here to represent it. And I'm going to connect it with the line all the way through, and maybe I'll erase this this tag here and I can replace it. So I'm going to put my arrows going up, arrows on the end to represent that it extends infinitely in the positive direction upwards and to the left and right. And now we can do our labeling here. So I could label this as the new function, or y is equal to 2 times x minus 3 all squared plus 4. And then I can label my black graph as y is equal to x squared, or the original graph. All right, now something to mention here that's on this page is the mapping notation. Mapping notation is the way in which we can take our function and then represent the order in which things are happening, and you can put them all together or in certain steps. So what they've done in the mapping notation is they've taken the original function, which is always labeled as, we take whatever our original points are as x, y. We can then do our vertical stretch, which they've shown by this factor of 2. In the third step, they put it all together by adding the 3, putting it 3 units to the right, and adding 4, putting it 4 units in the positive direction upward. Now, we're going to play around with that in some examples coming up here. Just know that mapping notation gets very popular throughout the 20 level and the 30 level. So we're going to use this a lot to represent what is the proper order, and, well, not only the proper order, but what is actually happening to the original points to get to the new points. Okay, now let's flip our page here. A summary of the transformations. So we had, first and foremost, the base parabola, which is always described as y equals x squared. This is that simple parabolic shape, or that U shape that we saw. Now, from there, what we had is we could alter it by vertically stretching it by multiplying by a factor of a to all the y values. And we had certain characteristics where we were like, it will get narrower in this case, or taller if the a value is greater than 1, which means that all the y values were being rapidly multiplied. We had values between 0 and 1, which were those fractional values. Fractional values flatten the graph or compress the graph. And then when we look at when it was less than 0, we called this a reflection about the axis because it now opens downwards. It flipped. Now, in the case of x minus p, remember there's the trick here. It translates by p units, but it's always opposite of what we see in here. And the trick around was because the negative already exists in here. So if I put a positive here, then the positive times the negative will just give me a negative. So that's why when it goes 3 units to the right, it's actually negative. And vice versa, if this was a negative already in here, and then there's a negative p, we know negative times negative is positive. And so if it ended up being less than 0, the graph actually shifted to the left. All right. And then with Q, there's no trick around this. If it's positive, you go up. If it's negative, you go down. Okay, let's look at class example 1 here. Describe the transformations and how the graph would ultimately compare to the original function of y equals x squared. Now, to describe the transformations here, we're just going to put a simple sentence in that specific order, just like we did on the first page. So let's say I look at this first one here. Well, I want to analyze the vertical stretch first, because remember, by our SRT rule, stretch, reflection, translation, we need to do it in that specific order. Let's start off with the a value. In the case of this first one, a value is 1, or more importantly, it is positive 1. And if it's positive 1, then not only is there just no stretch factor, because anything multiplied by 1, it's just itself, but at the same time, we see this as there's no reflection. So realistically, I'm going to leave those ones off. Or actually, I could even maybe just put a light sentence around this. So for the vertical stretch, or for the VS, it's by a factor of 1. About the x-axis. When it comes to the stretch, well, there's just simply no, or not the stretch, but the vertical reflection, which I'm going to call VR, there is just none. So I'm going to put a circle with a line through it because we do not reflect. When it comes to the translations, let's do the horizontal first. If it's positive 8, it's actually, we move 8 to the left. So we're going to say it's a horizontal translation, or an HT, by 8 units to the left. There we go. And then when we talk about our vertical translations, or our VT, it's by 4 units down. Remember, no special trick around the vertical translations. You don't have to put an opposite sign. It's only when it comes to the x value in between here. Okay, let's go to example B right below. Now, what I'm going to do is I'm going to recommend that we write this in a little bit different of a way. I want you to write this as y is equal to, and then instead of it just being 5x squared, I want you to write this as 5x plus 0 all squared plus 3. As you can see, what's x plus 0? It's just x, but this helps us see that it just means that there's no horizontal translation. We're not shifting left or right for this graph. Now let's work through all our different transformations here, starting off with our stretches. We're going to go, there is a vertical stretch, or a VS, by a factor of 5 about the x-axis. That part is very important. In terms of, is there a reflection? Well, there's no negative out front, so definitely no negative reflection. So I don't have to, put a vertical reflection. The VR, again, we could put a circle with a line through it, just being like there is none. If you want to write none, that's okay. When we talk about how much are we shifting left or right, there is no horizontal translation. So I'm going to put HT. This is null as well. And then in terms of the vertical translation, well, the vertical translation is just all of the points move up 3 units. So vertical translation of 3 units up. Perfect. All right, let's go to example C here. So we go over to C, and we see that the function looks slightly different than what we've dealt with before. To avoid confusion, what we're going to do with this one is I want you to minus 3 from both sides. Now at the 30 level, you'll see this a lot, where it's going to be y plus some value, and then over on the other side, it will just have the stretch factor with the reflection in the x. They like to do this to almost throw you off a little bit, but just know that this still means we're dealing with the same type of functions. They just put the q value over on the left-hand side. So when we rewrite this by subtracting 3, it's going to be y is equal to negative 2, x plus 5, all squared, and then minus 3 over here. Okay, and then just to clean this up a little bit, I will make sure the minus 3 is directly below and not cutting that piece off there. There we go. So minus 3, minus 3. Now, here's our different way of seeing this. When we go through our order in which of the transformations occur, we want to deal with the stretch first. So first and foremost, we're going to go, there is a VS, or a vertical stretch, of, or by a factor of 2. And then not only is it a factor of 2, but it's about the x-axis. remember from the previous lesson, what we talked about is that this about the x-axis piece means you're either moving away from the x-axis or you're moving closer to the x-axis. So it's in relation to the x-axis. That would almost be another way to phrase this, but it's just very commonly put about the x-axis or in relation to the x-axis or even just simply in the x-axis. I've also seen that. So instead of about, you also may see, and I'm just going to underline this piece here, you might see in instead, in the x-axis. Now, in terms of our vertical reflection, there is one, and it's because there's a negative. So now the graph opens downwards. I'm going to put that there is a VR, or vertical reflection, about the x-axis. Perfect. Now we want to go on to our translations, whether it be horizontal or vertical. Horizontal, we see it's positive 5, so it's actually going to be 5 units to the left. So let's make sure we write that down here. We have a horizontal translation by 5 units to the left. And then let's see if I got some space. Yeah, perfect. Just to confirm, I want to make sure I got this right. It was positive, yes, so therefore we're going the opposite direction. Lastly, we have a vertical translation of 3 units down, or a VT by 3 units down. Perfect. Okay, we're going to move on to D here. So in D, we see that we have everything listed as, okay, it's going to be y is equal to whatever sort of reflection stretch, and then our translations. All we have to do is list them. We don't have to play around with this equation at all. I'm going to start off with my stretch. There is a vertical stretch, Vs, by a factor of 2 over 5. And then what we always have to end it with is, not only is it a vertical stretch by a factor of 2/5, but it is about the x-axis. Perfect. Now we're going to go to our reflection. Because there is a negative here, we are reflecting about the x-axis. So we're going to write VR, vertical reflection, about the x-axis. When we go to our transformations, or not transformations, that's everything together, translations, we see that we have -1 in the bracket. So therefore, our horizontal translation is going to be +1 units to the right. So we're going to write our HT by 1 unit right. And then in terms of our vertical translation, it's 2 units down. So VT by 2 units down. Awesome. So whether it be A, B, C, D, all of these ones, you can clearly see we did the same order in which we approach them every single time. We use the SRT rule: stretch, reflection, translation. And so make sure you go in that order. If it helps too, you can think about it in terms of a stretch is multiplication. A reflection is a multiplication factor. A translation is addition and subtraction. By order of operations, you always start with the multiplication and then go to addition and subtraction to end every problem. So this is no different than what you would have talked about in previous math grades. We're keeping order of operations just in kind of a little bit of a fancier way with this more fancy language of stretches, reflections, and translations. All right. Now, moving into our next section here, or example 2, we're going to be tasked with putting the letters for each of the appropriate equations over on the right-hand side here. So they've given us a bunch of graphs all put together, or a bunch of parabolic graphs put together, a bunch of quadratic functions together. And they've given us the equations that they might represent over on the right-hand side, and we want to match up with the appropriate graph, which is always the letter is associated with in the top left of the graph. We want to associate this with these over here. So let's start off with the first one, y equals x plus 8 squared. Well, first and foremost, there's no sort of vertical translation. It doesn't go up or down, so it's along the x-axis. It doesn't have a reflection because there's no sort of negative here. It also doesn't have an a value which would multiply them. So all we're doing in this graph is moving 8 units to the right. or in this case, actually the left because it's negative, right? So I'm going to go over on my graph and I'm going to be like, which one of these starts at 0, which would be the original function, and then moves their vertex point over to -8? It's this one here. The first one is A. It opens upwards. It's only moved 8 units to the left. So I'm going to write the letter that corresponds is A. Now, in the opposite case, we see that it's y equals -x plus 8 squared. This translation, or the horizontal translation, is the exact same. We're not changing that we're moving the 8 units to the left, but what does that negative do again? It reflects it about the x-axis. And if we know that that's the case, there's only one option. It's h down here. So we're going to go to our box here, and we're going to fill in that the graph is h. Now, for the third one here, we have x plus 5 plus 4. And if we see the plus 5, we know we have to go 5 units to the left. So we're going to end up 5 units to the left. So that narrows down our options to the following. If this is -5 right here, then in fact, there actually only is one option, and it's this one up here. It's B, because there's no other graph that intersects or that goes at -5 here. So because this is the only graph, realistically, it's the only one, but let's actually show that. If I start at 0, 0, which is the original function, and I go 5 units to the left, and I go 4 units up, hey, look, there's my new vertex. Great. So I can put that this letter is going to be B. And make sure I go on the pen. There we go. Okay, now we have the opposite case scenario within the brackets. Instead of +5, it's -5, meaning I actually move 5 units to the right. However, the Q value is still +4. So it should look pretty much the same, just in the opposite direction. Hey, look, if this was when it was positive, this is going to be when it's negative. We go from our origin, which is the original point, 1, 2, 3, 4, 5 to here, and 4 units up. Therefore, G is the graph. Okay, let's plug that in here. Now, in terms of x minus 2 and then -1, that means we're going to move 2 units to the right and then 1 unit down. But in this case, there's actually 2 options here. And so we need to be very, very careful. When we go over here and we go to this point, we go over 2 and then down 1, it puts us right here on this graph. What we need to realize is that one of them is narrower, which F is narrower. It's like more condensed together. It's more compressed. When we deal with E, which is the other graph that could possibly be at this position, it looks more like the original. Now, what I want you thinking is, if there is no A value here, then it's not going to get narrower, so it still has to follow the property of it's going to start at whatever the origin point is, and then we should get a point that is 1 and 1 away, 1 and 1 away, because there is no sort of vertical stretch that causes this thing to get narrower or wider. And so if that's the case, then we know that this has to be E, based on the fact that all we've done is moved it left and right, and we haven't done anything about compressing or flattening it. Okay, we go into our next one. Well, this is an easy one because these two, the only difference is that vertical stretch. And we just said the vertical stretch will make it narrower, so therefore this would be the graph that lines up to it. We're going to say that that is F from our list here. So I'm going to go to my table and write in F. And let me try to make it as neat as possible here. There we go. Okay, for my last one here, or my second last one, we have 2 times x plus 3 squared plus 2. Well, that means there's a vertical stretch by a factor of 2, so all the output values are multiplied by 2. We have all x values are moving 3 to the left and 2 up. And so I'm just going to do that quick and see which types of options we have. We go from the original, 3 units left, and then 2 units up. So that would put us roughly about here. And then just to confirm that this would be the case here, what we can easily do here is say, well, if the multiplication factor, or if the A value is 2, then if I'm here, this would be my origin point. 1 and 1, this should get multiplied to 1 and 2. And same thing on the other side. It gets multiplied by 2. Yes, in fact, that would be the graph that lines up with this expectation. We're going to say it is variable D here. The graph should be narrower than the original graph because the vertical stretch factor is where A is greater than 1. And just to make sure I get my labeling right here, it was D. I almost put G there, just thinking that of a different graph. So we're going to put in D here. Okay, now last graph, only difference is that instead of it being the vertical translation up to, now it's down to. Well, there's only one option for that, and it's this one here. Because if we go from 0 to -3 and then down 2, here we are. And then just like we saw before, that the next 2 points were a vertical stretch by a factor of 2, this lines up from our original graph. We see that it was got narrower than that x squared graph. Let me just get my variable here. It is graph C, because we always look at the top left here. So we'll put C. Excellent. Okay, we've filled these all out. So you can clearly see how even when we mix them all together, it still is quite easy to identify them. Even if there's like 10 different graphs all put together, you can quickly put together which graph is the appropriate graph based on if there's stretches, reflections, or if there's translations that put it in a certain position. And what I would always think about when you're dealing with these graphs and matching them is what would happen to the original 0, 0 point? Always start at the origin, because our original graph has a minimum of 0, 0. And then it kind of looks like this, where it's 1 and 1 and 2 and 4 and 2 and 4, and it swoops like this. But if you just focus on just the origin, it will actually, through the transformations, put you to where the new origin is. Or not the new origin, but the new vertex point, just to be very clear. All right, let's look at example 3 here. So the original parabola, y equals x squared, is transformed as described below. Its image equation has the form y equals ax minus p squared plus q. Determine the equation of the transformed quadratic function based on the description. Okay, so we're just going to take that original equation, which is this piece here, or our vertex equation, and we're just going to plug in components based on what they give us. And if they're not given to us, then it will just simply be 1 or 0, depending on what's happening here. So let's say we look at the first one here. They say it is reflected in the x-axis, or you could say about the x-axis, and then translated 4 units right. Okay, so there's no sort of vertical translation, but there is a reflection and some sort of right movement. Now, to put this together here, we're going to write it as, therefore, we know it is going to be y is equal to, it must start with a negative, and the reason is because it's reflected. So the negative means that this is reflected about the x-axis, or all y values become negative. In the bracket here, we're going to write this as x, and then because it's 4 units right, we're actually going to write this as positive, or no, as negative. But if we write it as negative, I just want to show you something quick. If I put this as a negative, and we actually know that it is 4 units to the right, or that is positive, plus 0 for q. I'm just going to throw that in there just to demonstrate this. In our actual line, or therefore, we can write this as y is equal to negative x, a double or a negative and a positive together like this, it's going to become negative. So you can put negative 4 and square it, and then the 0 we don't need to put on the outside. Here's our equation. Now, what does this mean our a value is, our stretch factor? It's simply just 1. They didn't give it to us, so I'm not going to put it out there. We also know that there wasn't any sort of up or down movement, so therefore the vertical translation, or the q variable, is just 0. We only have this reflection and the movement of 4 units right, which of course we see is the opposite sign in here, which I've demonstrated again why that is here. All right, let's look at B. It's stretched vertically by a factor of 1/4 about the x-axis, and then translated 4 units down. Okay, so instead of having a horizontal translation, now we have a vertical, and we have a stretch factor instead of a reflection. So therefore, let's write that in below here. Therefore, y is equal to, well, the 1/4 is going to go out front, no negative because it's not reflected about the x-axis, and then it's transformed by a factor of 2 units down. So we're going to look at this and say it is 1/4 x squared, and then minus the 2q value on the outside here. And then again, we could view this as the following. If you really, really wanted to, we could say, oh, well, it's 1/4 and then x minus 0 all squared minus 2. But this is kind of irrelevant. If we don't want to put this there, we don't have to. This is basically just saying that there is no horizontal translation. But if there's no horizontal translation, let's just leave it out and just keep it as it's just x squared. All right. Example 4, we're going to look at an example where we have a point that lies at 3 and 9, and it lies on the original graph of y equals x squared. Remember, anytime you see f of x equals x squared, this is just another way of saying y is equal to x squared. So don't be fooled, f of x is just equal to y as well. It's the output variable. Describe what happens to the point when each of the following sets of transformations is performed in the order they're listed. Identify the corresponding point on the transform graph. Well, now here's where we're going to go into the mapping notation, because the mapping notation is going to really help us clearly outline what is happening to each variable so that we can take an original point and then get a new point right from it. So here's what I mean by this. Let's read the sentence first and foremost. There's a reflection in the x-axis. There is a translation 4 units down and 7 units left. Now, what this is going to do for us is the following. We look at this and we're like, okay, we want to take whatever the original point is on the original graph and map it or transform it to be this new point. What is the new point? Well, let's see what happens with the x value first and foremost. If there's a reflection in the x-axis, then the negative is going to go on the y, so we don't need to worry about that happening to the x. The translation of the 7 units left, we can report this as the following: x minus 7. Now we're going to put a comma because that's all that happens to x, is it just goes 7 units left. In terms of the translation or the transformations that happen on y, we know it's going to be negative y because it's a reflection first and foremost. And once it's been reflected, we're going to go 4 units down. So negative y minus 4. Now here's how this helps us. Let's actually see the point in action here. So we're going to go 3 and 9, or the input and the output. When it's mapped, here's what it's going to look like algebraically. We write it as 3 minus 7 in the x. On the y, we're going to write this as negative 9 minus 4. Let's simplify what this becomes. In the first bracket, it's going to be negative 4, or in the first point, the x is going to be negative 4. In terms of the y, it's going to be negative 9 minus 4. Negative 9 minus 4 is negative 13. Close the bracket. There's the corresponding point of where it's been transformed to. Perfect. Okay. Now, if we really wanted to, we could annotate this in the following way in the notes. So we could say this is our original, and then this is the new. You don't have to put that in there, but that might just help you track like where we started, where we went to. Okay, we're going to do the exact same thing just one more time with different types of transformations. A multiplication of the y value by a factor of 2, aka a vertical stretch by a factor of 2, followed by a reflection in the x-axis. All right, this one's a little bit easier for us. So what we're going to do is, again, we're going to start off with our xy, which then is mapped to the new point. Well, nothing's happening with x because they didn't describe anything affecting the x variable, so we're going to write it as just x. For the y variable, we're going to write it as, well, it was reflected, so there's going to be a negative, but the y's were all multiplied by 2, and so we're going to write it as x comma negative 2y. Now let's take our original point of 3 and 9. So 3 and 9, we're going to map it to the new point here. So this is 3 for x, negative 2 times the 9 for y. I'm going to close that. This is going to give us a final point of 3 for x, and negative 2 times 9 is negative 18 for y. Again, what we could put here right below is we could be like, this is the original, and then this is the new point. Perfect. So mapping notation, as you can see, it gives us this really nice ability to take an original point and then just directly algebraically plug it in and say, hey, what is the effect of all of these different transformations at once on these points? All right, now let's go to our next example here. So this is all dealing with finding equations based on a description of things that happen within any given quadratic function. So determine the equation of the quadratic function that has the given characteristics. Let's start off with the first one. Now they're all going to look a little different, so be aware of that. Here's what the first one says. With a vertex point of 0 and negative 9 and passing through a specific point. Well, this is just another way of saying, remember from lesson 1, our vertex is always P and Q, so you can put that in the bracket. When it says passing through a point, this is just another way of saying this is a specific x and y. Now, if we before we move any further, what I really want us to do here is I want us to put an arrow that goes to this top line here. So finding the equation of a quadratic function given this description or given characteristics. Our number one goal is to find the a value first and foremost, or the vertical stretch. So number one goal, find the a value. Now, I say that because unless it's specifically given within the problem, which it often isn't, the a value is the stretch factor, and if it's not actually appropriately put into the equation, we may just think, oh, there's no stretch factor, but that's not true. When we have these descriptions, we need to figure out what is that stretch factor going on if it's not given. So that's our whole goal here. We have a p and q, we have an x and y in this first one, and number one goal, let's find the a value. So let's do that. we're going to start by putting together the original equation in terms of vertex form. I want to write it as y is equal to ax minus p all squared plus q. This is directly off your formula sheet, so don't feel like you have to memorize it. Now what I'm going to do is plug in the p, q, x, and y. The y value is 7. The a value is what we're looking for in order to build out our equation. We're going to then write in x, which in this case was our -4, minus the 0, which was at our x value for the vertex, all bracketed and squared. And then we're going to take our -9 and put it in for q. Now let's do a little bit of simplification here. This is going to become 7 times a. -4 squared is going to become 16. So I'll write 16 within the bracket, -9. In order to isolate for a, I'm going to first of all have to add 9. 7 plus 9 is equal to 16. So this is 16 is equal to a multiplied by 16. And then what I have to do to wrap this up is divide both sides by 16. Excellent. So therefore, we get an a value equal to 1. So what does this mean? There actually realistically is no vertical stretch, but that's not always the case. We can't just assume that. We do have to solve for this in all of these cases, because if you just assume, oh, a is equal to 1, you may actually be describing a totally different graph. Now, this makes our job very simple because now we just need to wrap this up by taking out the x and y and writing it in a more general form. Therefore, y is equal to 1, which is a. We don't really need to write that. Bracket, we're going to write the x, and then we know our p-value was 0, so theoretically this is x minus 0 squared. We know our q value is 9. When you go to write the equation in the end, like we're doing, please do not write a specific x and y ordered pair. That is not effective with this. In fact, if we're describing a function or a whole graph, it must be that we have the ability to input a different x, input a different y. Now let's just take this one step further, simplify it. Instead of x minus 0, I'm just going to make this x squared minus 9. So in fact, when we look at this overall, there's not much happening to the original function. The only thing that happens to the original function is we're just lowering all the y values by 9, or we're doing a vertical translation by 9 units downwards. All right, let's repeat this for the next one with different characteristics. So we have a vertex at -1 and 4 and a y-intercept at 2. Now, when they say we have a vertex, again, we always want to write it as this is our p, this is our q, so that doesn't change. When they write the y-intercept, this is where it's a little tricky. When we have a y-intercept, it is always that the x value is 0. Your opposite value is always 0. So what we're going to do is we can write this as an ordered pair of the following. This is going to be 0 for x, 2 for y. Any sort of y-intercept, the x value is always 0. Any sort of x-intercept, the y value is 0. Now, this gives us an ordered pair, and, or more importantly, I could even write this as this gives us an xy, or a specific xy we can use. The other pieces are vertex p and q. Let's repeat the same steps we did before. We're going to solve for a. Y is equal to a x minus p all squared plus q. We're then going to write in all the values we found here. So the y value is going to be 2 for the y-intercept. The a value is what we're looking for. The x was 0. The p-value was -1, so therefore it becomes +1 squared plus q in this case, which was +4. Now, I feel the need to actually show this within the brackets here, so I'm going to quickly do this. The negative already exists there, but if I put a -1 in the brackets, here's what it's going to do. I'm going to write the next step. 2 is equal to a, 0 plus 1. All squared. I think it's really important to just show it on the first one, again, of how we take a negative value for our vertex or axis of symmetry, and then it becomes positive. Now, using some simplification, we're going to write this as 2 times a. Well, 1 squared is just 1, so this leaves us with 1 plus 4. Just like we did in the previous one, before we divide by 1, in order to get the a alone, I have to subtract 4. When I subtract 4, I'm just going to continue this slightly off to the side here. Let's see if I go right here. I think this should be okay. So 2 minus 4 is going to be equal to -2, which is equal to a times 1. And then we know when we divide anything by 1, I mean, that's just going to be itself. So in this case, our a value is equal to -2. Now, this is kind of interesting because what this reveals to us is that we actually have a vertical reflection about the x-axis. So our graph, instead of opening upwards, opens downwards. Now we want to summarize this into an equation. So we're going to say, therefore, off on the side here. Let's do that off on the right here. I'm going to go, therefore, Instead of putting in a specific y, we're going to write it as a general y is equal to the -2 we found for the a value. In the brackets, we had an x value at our vertex of -1, so it became +1. It's x plus 1 all squared. And then our q value was +4. And so we shifted the graph up by 4 units, or a vertical translation of 4 units in the positive direction upwards. All right, there is our answer. Again, you want to always have it where it's a general y and a general x, because we should always have the ability to describe the entire graph and not just a specific key point of the graph. So this is how it should always look, where you have your q, you have your p, and then the x and the y are left as is. Okay, now going down to this description here. We have a maximum value of 12 and an x-intercept at 3 and 15. Now, this one's a little bit tricky in the sense of here's what's actually going on, and I highly encourage you to just draw a graph of this just to see what it actually looks like here. So if I was to graph this, I'm going to draw a basic Cartesian plane in the following way. I'm going to write where we have a maximum value. Maximum meaning this thing faces downwards. It actually opens down. I'm using more formal language. It opens downwards. And then on top of that, we have x-intercepts at 3 and 15. I'm going to put this little 3 here. I'm going to put 15 here. And then I'm going to put a point somewhere kind of in the middle up here at 12 in the y direction. So this is going to be our 12 up here. Now, our parabola would look like the following. If I was to sketch over top of this what this parabola looks like, maybe I'll use red to help us out. I'm going to go from here. It's going to go through here and keep going down. It's going to go through 15 and then head down like this. Now, you're probably thinking, okay, so we have the y value in terms of the overall, because anytime they say the maximum or minimum, they're always describing the y. So if you need to, I would even underline that here on the note here, or even you could just highlight that maximum value. This is another way of just saying the y is equal to 12. And I'll make that a little neater here. There we go. And then the x-intercepts, anytime we have an x-intercept, the y values at these are both equal to 0. So if we're able to figure out what these are in terms of coordinate points, well, they're the following. I can write the first one as and maybe I'll even write this y off to the side just to kind of clean it up a little bit, y equals 0. I'm going to write this as 3 and 0 as 1 point, and I'm also going to write this point as 15 and 0, because for both of these, the y value is 0. What did this just give us? It gives us a specific xy. So this is xy, this is an xy. Great, that helps us out a ton. Now, the only thing we need to figure out is what is this vertex? Well, the vertex, in terms of a p and q, we need to figure out what the x value is. So far, we have the maximum, which is the y value of 12, but to complete this as a point of p and q, we need that x value. We're going to take the average. So here's what we're going to do. Off to the side here, write in the following. If I want the average, or whatever will be the axis of symmetry, remember, because the axis of symmetry is that x value that divides the graph in half, we want to figure out what is this specific x value. Well, we're going to have to take the average of the points. So I want you to do the following. What is 3 plus 15 all divided by 2? Well, that's the same as saying that this is going to be equal to 18 divided by 2, and 18 divided by 2 is 9. Okay. So this is our average, and just to keep space for our rest of our problem here, I'm just going to move that off to the side here. There we go. And now, instead of it being x question mark, I'm going to put that this is x positive 9, which is our axis of symmetry equation, or equation of the axis of symmetry. Instead of a maximum value just being y equals 12, I'm going to now write it as we have an x value of 9 and a y value of 12, and this is our p and our q that we're looking for. Okay. And again, just to kind of clean this up, I'm going to just move this down just a little bit here just to avoid the confusion there. Okay, now here's where it actually comes to solving the problem here. We need to solve for our a value yet again. So to solve for the a value, let's do that here. It's going to start with y is equal to a x minus p all squared plus q. Now, here's where we get to choose an x and y. So it can either be the 3 and 0 or 15 and 0. I like to keep the numbers simple, so let's use 3 and 0. And we're going to plug in our p and q here. So for y, it's going to be 0. For a, that's what we're looking for. Our x value is 3. Our p value is positive 9, so it's actually going to be minus 9 all squared. And then our q value is positive 12. Now it's going to be 0 is equal to a 3 minus 9 is negative 6. Negative 6 squared is going to be equal to 36. Plus 12. I'm going to subtract the 12 across because I can't divide by that 36 to isolate for a otherwise or until I've done that. So that's going to give me, I have negative 12 is equal to a times 36. And then what I need to do here is divide both sides by the 36. So this will be, and I'm trying to make this as neat as possible. Let me shift this all up here just to create the space to do that division. So I'll shift it here. Great. I'm going to divide both sides by the 36. What is 12 divided by 36? Well, this is simply just 1/3. And more importantly, it is negative 1/3 for the a value. So this means not only is there a vertical stretch, but there is also a reflection about the x-axis. Now, to summarize this all together, remember, we don't want to put in a positive x or y, or more importantly, not a positive x or y. We don't want to put in an x and y. We want to leave it as generally y is equal to that a value of negative 1/3. Let me clean up that 3 here. And then multiplied by our x minus whatever our p-value is. In this case, it was 9. So we're going to go x minus 9 squared. And then for this, at the vertex, it was shifted up 12 units. There's our equation. Perfect. So let's highlight it and wrap that piece up. Okay, now we're going to go to our last example of this, where we're given characteristics. We have a y-intercept at 20, so meaning it's at 0 and 20 in terms of a point. We may as well write that in here. Anytime we have a y-intercept, it actually means that our x value is equal to 0, our y value is equal to 20, and this gives us a specific xy to deal with. The axis of symmetry is x equals 3, and it is passing through the point 2, 4. Okay, now 0.24, again, this is going to give us some sort of x and y. And in terms of the axis of symmetry, this is half of the p and q. Remember that the axis of symmetry gives us the p value, so technically we have 3, we just don't have the q value. So we're going to need to figure out what is that q value before we actually begin this. Now this might involve a couple steps, but what we're going to do is we're going to tie these together in the following way. We're going to start off by dealing with these two together in one equation, and then we're going to start off with dealing with these two in the second piece, or we're going to end with those two in the second piece. So let's write out our first equation here. Y is equal to, and it's going to be a x minus p all squared plus q. We're going to build out our two equations based on this. So our first equation, we're going to use the y-intercept and the axis of symmetry. So this is going to give us the following. Our y value is going to be 20. Our a value is what we don't know. Our x value for this was 0. Our p value was 3, or negative 3, because it's always opposite of what we were given. Our q value was equal to plus q. Now, what we want to do is we want to pair together the other two to build a secondary equation to help us solve this further. So we're going to pair up the axis of symmetry and the secondary point. That means that my second one is going to be 4, which is the y value a. X was equal to 2 minus 3 all squared plus q. Excellent. Okay, now let's simplify both of these. So if this is the overall system of our equations based on the descriptions of part 1 and part 2, then what we're going to do is in the second line, I'm going to write this as 20 is equal to a. 0 minus 3 all squared is actually equal to 9 plus our q value. The second row is going to be 4 is equal to a times 2 minus 3. 2 minus 3 is negative 1. So this is going to be a to the 1 when it's after it's squared plus q. Now what we're going to do here is we're going to eliminate the q so that we can solve for the a. Because if this is a system of equations and this is what it boils down to, let's use our elimination method from grade 10. I'm going to put a minus. I'm going to underline these two. And the reason I'm putting minus is because if I take q and subtract q, this should eliminate those for us. So 20 minus 4 is equal to 16, which is equal to 9a minus 1a, because if I rewrote this, it would be 9 times a, 1 times a, 9a's minus 1a. This is going to give me 8a's, so I'm just going to rewrite it for this piece here. I'm going to divide both sides by 8, divide both sides by 8, and therefore this is going to give us a vertical stretch factor of a being equal to 2, or 16 divided by 8. So this is good. We've found the a equals 2, but it's not good enough to wrap up the problem yet because we still have this unknown q value. Well, to get the q value, all we do is just go back up to one of these equations and plug in the a value. So let's do that in the second equation. Why not? It doesn't really matter which one we do, but if we break it into steps, here is step number 1. Step number 2, I'm going to take that and plug it into the second equation. So this is using a substitution method. We're going to write it as 4 is equal to, we have a value which is 2, so I'm just going to write it as 2. I'm not going to put it in brackets. We have our x, which was 2, minus the 3, all squared, and plus q, which is now our unknown variable. I'm going to write this as 4 is equal to 2 minus 3, again, is negative 1. Negative 1 squared is just 1 plus q. I'm going to subtract away the 2 because we have this 2 that we need to get rid of on both sides. That means 2 is equal to q. Or we could write it the other way and say, sometimes we like to write the variable first, q is equal to 2. Now what this allows us to do is wrap up the problem. Here it is. Part 3, we're going to write our final equation. Y is equal to the a value, which was 2, x minus 3, which was the axis of symmetry, squared, plus 2. There's our final equation, given the fact that we now have an a and we have a q value. So as we zoom out here, you're going to see that this is quite involved, right? There's a couple things we need to do. We need to build out the two equations, simplify them using a system of equations, and then substitute to figure out those two variables or to make sure we have q and a. Once we have q and a, well, we can put them together. So these two-parters, they're a little difficult, but lots of practice would help you out with these. I can answer as many questions as we need to if you see these within the textbook or any sort of future practice that you're dealing with. Okay, now let's look at our final page here. Finding the equation based on a graph. So on the previous page, it was all based on description. And our number one goal was to find a. It's no different. In fact, I'm going to literally just take this line and copy it over to our next page. So I'm going to copy this here, hold this down. There we go. Perfect. We need to find the a value always. So rather than it being by description, now it's going to be based on the graph. Let me make sure I paste that in here. Perfect. There's our number one goal. Awesome. Okay, so now based on the graph, here's what we need to do. First of all, we need to figure out where's the vertex. We then need to use a secondary point to give us an x and y. Then we can solve for a and build out our equation. So let's label it on the graph here. If I go to my vertex, it's actually right here. This is -3 and 0 for y. In terms of the points, they actually gave us two that we can use, one here and one here. So let's say we use that first point, or this one right here. I'm going to write that this is at -1 for x, -2 for y. Now, to be more specific, as we look at step 1 here, I'm going to write the following in. We have an xy, or a specific point, which is at the following. It is at -1 and -2. We have our vertex of P and Q, which is at a specific point of -3 and 0. Now we can start off our step number 2, which is let's solve for a. Step number 2, I'm going to write out the original equation, which I always recommend, y equals a x minus p all squared plus q. I'm then going to plug in the specific points of x and y and p and q. So for my y value, it's going to be equal to -2, which is equal to a. X value was -1. P was -3, but because it's negative, it's actually positive in the bracket. And then the q value was +0, which kind of keeps this simple for us a little bit. I'm going to simplify. -2a. In the brackets, it's -1 plus 3 is 2. 2 squared is 4. And then we can just leave out the 0. Now I'm going to divide both sides by the factor of 4, or this element of 4. And then this will give us an a value when reduced of a being equal to -1/2, because both 2 over 4 we know just reduces to 1/2. Okay, we have the a value, therefore we can just summarize this all in a statement of we know we want to keep it as the basic y. The a value is -1/2. The x will go back in as just x. The +3 was the axis of symmetry, and then our q value was 0, so technically we don't need that. We're good. We can just highlight this as the solution, and we're done. Perfect. So again, number one goal, always find the A value. What changed from our last page to this page, rather than being just given the points and the information, now we have to find them on the graph and point them out and then use them to help us solve in the exact same way. Okay, one more example of this. I'm going to go down to the following graph here. We look at this and we see that it opens in the upwards direction. We want to analyze this and figure out, well, what is the vertex? It's right here. It's a minimum point. I'm going to write this as we have at 2 for x, 1 for y. I'm going to choose this point, our further out point of 3 and what is this, 5? Yep, perfect. Now for step number 1, let's just be very clear about what these points are. Our x and y are just our random point we pulled from the graph, was at 3 and 5. Our p and q, which is our vertex point, we pulled this as 2 and 1. And then step number 2, we want to solve for the a value because we don't know what the vertical stretch factor is. Y is equal to a x minus p all squared plus q. Remember, you always want to write the general formula out. It's on your formula sheet. You do not have to memorize this. I would always start there just so that you can now fill in the blanks. Our y value is 5, so 5 is equal to the a, which we don't know. Our x value is 3. Our p value was 2, but because it is positive, now it's going to be negative. And then our q value is positive 1. Okay, let's simplify this. 5 is equal to a multiplied by, well, 3 minus 2 is just 1. 1 squared is simply 1. Before I can divide by that 1 or get rid of the 1 on the a, I'm going to subtract 1 from both sides. This is going to give me that 4 is equal to a times 1. And we know anytime we divide anything by 1, it just results in the number itself. And so we can say that our a value is equal to positive 4. All right, now to summarize this, we're going to put it in our equation. Y is equal to a, which is 4, x, was it a positive or a negative? Let's just make sure. It was a negative 2 because we shifted to the right, squared. Our q value was positive 1, and there we go. So there was a vertical stretch, there was a horizontal translation, and there was a vertical translation. Excellent, there is our final form here. Now, something I want to point out with these, especially with the graphic ones, is I want you to be aware of the following. When we look at these on a broader scale, we can look at something very specific that I really want you to catch on here. When the a value is negative, the a value is negative when the graph opens downwards. Anytime the graph opens downwards, if you solve for a like we did and it's not negative, it means there was something wrong in the algebra. So please recognize that if it opens downwards, you must see a negative for an a value. If you don't, there might be something off. Maybe the value might be right, but you still need to make sure that that is negative. In the case it opens upwards like these ones here, the arms reach to the sky, you must have where the a value is positive when you solve for it. If the a value is not positive and it's negative, you're describing a graph that's the opposite. It's facing downwards. So we want to be very clear with that. The last thing I want to say about this in terms of a general pattern is, do you see our a value, our vertical stretch factor was 1/2? What happened to the graph from the original graph? It becomes more like flat or compressed out this way here. So we see that it flattens out in this way. It kind of flares, if you want to use that terminology. Whereas when the value was greater than 1, such as a being something like 4, we saw that it gets narrower, it's skinnier, it's more like compressed together like this. And so I know in the previous lesson they used compressed and expansion. Let's use the same terminology here. If a is greater than 1, it results in an expansion. All the y values are extended upwards vertically. Whereas when we looked at something where it's like a is equal to 1/2 like this, it means everything gets compressed or flattened closer to the x-axis. So if I had an original y value here, it gets flattened. If I had an original y value up here, it gets pushed towards the x-axis. So just some important things to notice as we look at these. Now, your homework is listed at the bottom here. These are the ones that I would like you to go through. I highly encourage you go through all of these to make sure you master the material, because putting all of the transformations together and then doing this characteristic work and this graphic work, it's not easy stuff on a first go through. So please just know that this is something that you're going to need to practice. There it all is in the bottom, your assignment 3.1 for part 2. All right, good luck.